Hello, students. This is the continuation of fourth module. Under fourth module, we are in the second chapter, that is media access control. This already we have discussed the random access protocols. Then controlled access protocols we have discussed. That is in the last session. That is reservation, polling, and token passing we have discussed, isn't it? So in this video lecturing, we will discuss the third one, that is channelization protocols. Third type of multiple access protocol, that is the channelization protocols. Under that we will see each one of this, that is FDMA, TDMA, CDMA. Frequency division multiple access, time division multiple access, and code division multiple access. We'll see one by one. Okay. The first one, before that, what is channelization? Channelization is a multiple access method in which the available bandwidth of a link is shared. Okay, that is the available bandwidth is shared, but how? In the form of time or frequency or through the code. On the basis of these three, the division is made between different stations. That is, the first one is frequency division multiple access. You are dividing it into frequencies based on the frequency. Time division, that is time slots. And code division multiple access, CDMA. Now we'll move on to the first one, that is frequency division multiple access, FDMA. In this frequency division multiple access, the bandwidth is divided into frequency bands. Okay, and each station is allocated a band to send its data. Here you have 4 stations, right? That is station 1, station 2, station 3, and station 4. To avoid interference, each band is separated by guard bands here. Okay, I'll tell you what it is. Here you can see that you have 4 stations. Thus 4 stations which I told you now. And this shows a total available bandwidth, that is here. This is the total available bandwidth. That is the difference between the F max and F minimum. As if this is F max and if this is F minimum, then the difference between this is the bandwidth. Okay, and these bandwidth are divided for different stations. See, here you have 4 stations, right? Station 1, 2, 3, 4. So the bandwidth is divided into 4 channels or slots. And these divided channels are specific for each station. See here, the first station, it is in blue color. This occupies the station 1. Okay, here the station 1 is, the data for the station 1 is sent using this bandwidth. Second channel occupies station 2. Third channel, that is this green line, occupies station 3. And the fourth channel, that is the pink line, occupies the 4th station here. Now, between these channels, there is a frequency which is left freely. That is, no data is transmitted between that frequency, and that is called your guard bands. Now, why we want this guard bands between 2 channels is because, say, it is to overcome the overlapping, or you can say to avoid interference. We use this guard bands which is between the stations. Okay, and in this we have 4 stations, so the number of guard bands used is 3. That is, always the number of guard bands is 1 less than the total number of stations. In this example, you have 4 stations. So the number of guard bands required is 4. That is between the stations 1, 2 and 3 guard bands you require here. Okay. So in frequency division multiple access, you can anytime any station can send the data, because each station has its own dedicated channel here. So anytime the station can send the data. Okay, so the stations cannot use the entire, that is one disadvantages, it cannot use the entire bandwidth. It can use only this part of the entire bandwidth which it is reserved for. Okay, only part of the bandwidth it can use to transfer its data. Next, we'll see to the second one, that is time division multiple access, or TDMA. What is TDMA? Okay, in this time division multiple access, the bandwidth is just one channel here. Okay, just one channel, that is time shared between different stations. Different stations. Here you have 4 stations, isn't it? 1, 2, 3 and 4. And this, in our previous one, that is frequency division, this is time division, right? In frequency division multiple access, anytime the stations could send data, but they couldn't use the full bandwidth, right? But here in this time division multiple access, stations can use the full bandwidth here. Okay, full bandwidth, but they cannot send the data anytime they wish, because they have time slots at particular time only they cannot, they can send their data. In this diagram you can see that you have 4 stations and bandwidth divided into 4 time slots. See here, 4 time slots: blue, yellow, green and pink. These are the 4 time slot. And first slot here, this is the first slot, is meant for station 1, this one, isn't it? Okay, second slot is meant for, that is yellow color here, is meant for station 2 here. This is the second slot. Third slot, that is this one, green color one, is meant for this third station. And the last slot for station 4, that is the pink color for station 4 here. Okay, now unlike your frequency division multiple access, the previous one, here we don't have guard bands, that is between the station between these slots, you don't have guard bands, but to compensate the delays, that is when you transfer the data in this time slots, if there is any delay, to compensate that, you have something called guard times, a time slot between these slots, they're called guard times. There in the frequency division multiple access you have guard bands, here you have guard times. Hope you understood. This is the common channel and this is the bandwidth divided into slots. These are the 4 stations and each color represents that each station where the slot for each station there. Okay, next we will look on to the third one, that is code division multiple access, CDMA, nothing but code division multiple access. In CDMA, one channel carries all transmissions simultaneously. That is, see, the advantage over the first one, that is frequency division multiple access, is that this code division multiple access utilizes the entire bandwidth. Okay. And the advantage over the TDMA, that is the time division multiple access, which we discussed, is the second one. is that this CDMA, that is code division multiple access, can send data simultaneous. That is, what is it? It uses the entire bandwidth as well as it sends the data simultaneous. Which one? This CDMA, that is code division multiple access. Now we'll see what is this code division multiple access. Okay. Again, here we have four stations: station 1, station 2, station 3, and station 4. Okay, and each station will have one unique code. Okay, that is for station 1 you have code C1, station 2 you have code C2, station 3 you have code C3, this one, and for station 4 you have code C4. And the data that is D1 belongs to station 1, D2 belongs to station 2, D3 belongs to station 3, and D4 belongs to station 4 here. Okay, now you have the, for each station you have code as well as data, right? Now you have to find the product of this at each station. That is for example D1 C1, product of each station D2 C2 and D3 C3. Product means you are multiplying the data into the code D4 C4, and in the channel we will send the algebraic sum. That is the sum of all this we will send in this common channel. This is your data which is sent through the common channel. It is shown here. Okay, D1 C1 plus this one, the product of station 1, that is D1 C1, plus the product of station 2, that is D2 C2, and product of station 3, that is D3 C3, station 4 D4 C4. Like that, if you have n number of channels, you have sum of all that n number of stations, product of all the n number of stations. Okay, here in this case we need to assume that the codes, these codes have two properties mainly. That is first one is, if we multiply each code by another, we get 0. See, for example, if I multiply each code, that is a C1 with the C3, I'll get 0. Second condition or the property is that if we multiply each code by itself, for example, C1 into C1, we will get 4. That is 4 represents the total number of stations here. In our example, it is 4 stations, isn't it? So when you multiply the code by itself, we should get the total number of stations as the product. Understood, right? Two properties, that is when you multiply the station in the code by itself, you should get the number of stations as the product, and when you multiply this code with the other code, you will get a 0. Okay, based on this we'll do the calculations. Now what are this chip sequences? Nothing but your code. Okay, code division multiple access is based on coding theory. Each station is assigned a code which is a sequence of numbers called chips. These are called chips. Chip 1, chip 2, chip 3, chip 4. That is, chip means codes for each station it represents. This is for station 1, station 2, station 3, station 4. In our example, okay. Now we will see to this one, each of these sequences, and inside the sequences you have these 4 elements. Okay, why 4 elements is because you have 4 stations, right? Station 1, station 2, station 3, station 4. That's why you have 4 elements inside each code sequence here. Okay. Now this chip sequences is based on some general properties, that is how to multiply the chip sequences. How you are doing the multiplication and addition we will see. First property is that strategy in this sequence, that is to select the chip sequence, is each sequence is made up of n elements, where n is the number of stations. I told you. See here in our example, this is a chip sequence, one chip sequence, isn't it? It is made up of 4 elements, that is +1 is one element, second element is +1, third element is +1, fourth one is +1. 4 elements equal to total number of stations. Okay. Now, second property is that if we multiply a sequence by a number, you call it as sequence, that is scalar multiplication. Okay. In that case, every element in the sequence is multiplied by that element. Say, for example, 2 into the chip sequence. This is a chip sequence with 4 elements. In that case, you have to multiply 2 into 1 plus 2, 2 into plus 1, that is plus 2, 2 into minus 1, that is minus 2, 2 into minus 1, that is minus 2. Okay. Third property, if we multiply two equal sequences, that is you have to number of elements is the same in both the sequences, then you have to multiply element by element and add the results. If we get n, where n is the, and you will get one number, right? This number is equal to the number of elements in each sequence, or you can say number of stations also. This is called the inner product of two equal sequences. An example is given here. You have two sequences with the 4 elements each. +1, +1, -1, -1, first sequence. Second sequence is +1, +1, -1, -1. And when you multiply these two, what happens is, first you have to multiply this first element with the first element in the second sequence. That is +1 into +1 is +1. Okay. +1 into +1, second element in the first sequence and second sequence is a +1. Third element in the first and second sequence, that is -1 into -1, that is +1, again multiplication, right? Again -1 into -1, that is +1. Now add this together, you will get 4, which is equal to the number of elements in the sequence or the number of stations. Next property, if we multiply two different sequences, this sequences are different, right? See, +1, +1, and less 2 is -1, -1. Here +1 and followed by +1, +1. That is, I told you, code. You are different, multiplying it with the different code. C1 with the C3, if you multiply, you will get 0. In the previous property, it was these two sequences are same, isn't it? That is C1 with the C1. You will get 4 in that case, multiplying by itself. Okay, now here multiply two different sequences element by element and add the results. We get 0. This is called inner product of two different sequences. For example, you have the first sequence, that is +1, +1, -1, -1 into, multiply it with +1, +1, +1, +1, all +1. What you will get? +1 into plus into plus, +1, plus into plus, second is +1. Now the third element in each sequence, that is -1 into +1, it is -1, and the fourth element in each sequence, -1 into +1, you will get -1. Now add these, 1 plus 1, 2, -1, 1, -1 is 0. add this sequence, you will get 0. That is, you are multiplying a code with a different code, you will get 0. Next property is adding two sequences means adding the corresponding elements. The result is another sequence. For example, see, when you add these two sequences, you get one more sequence here. How to add? Corresponding elements you have to add. That is, first element from sequence 1, first element from sequence 2. Second element from sequence 1, second element from sequence 2. Next, third element from sequence 1, third element from sequence 2, and so on. Okay. How we are adding? First element plus 1, you will get plus 2, plus 1, plus 1, you will get plus 2. Next, minus 1, plus 1, addition, will get 0, right? Minus 1 plus 1, when you add, you will get 0. Hope you understood how we are going to do the addition and multiplication in this CDMA. Okay. Now, next, we'll see the data representation in CDMA. That is code division multiple access. In code division multiple access, data bit 0 is represented by -1. Bit 1 is represented by +1, and silence is represented by bit, and that is 0. Okay, that is which has no signal sent. Silence means no signal sent. Okay. Next, we will see the sharing channel in collision code division multiple access sharing channel. How what is sent? Here is the example. Here the third channel here is silent, that is no data is sent. Okay, now the data in the channel, here it is the addition of all the sequences. Now we'll see how what is generating the sequences. See, station 1 has data bit 0 to be sent. Station 2 has data bit 0 to be sent, and station 3 has no data to be sent, so it is silent. Okay, and station 4 has bit 1 to be sent. Now, how the bit is represented when encoding? We have to transfer the bit, isn't it? While encoding, this 0 is represented as -1. Same here, 0 is represented as -1. Here it is 0 itself, silent. So 0. And 1 is represented by +1. Okay, this is the encoding. Next, for each, this is the data is ready now. Next, for each station you want code, right? That is C1, C2, C3, C4. C1 is +1, all +1. 4 elements you have because you have 4 stations, 1, 2, 3, 4. 4 elements. Code 1 is there, and for station 2 you have code 2, that is +1, minus, plus, minus. Next, for station 3 you have code 3, plus, minus, minus. And for station 4 you have plus, minus, minus, plus. Okay. Next, what you have to do, once if you have the data and the code, you have to find the product of data and code, isn't it? That is D1 into C1, -1 into all this, -1, -1, -1, -1, you will get. That is the product of data and code. Same here, -1 into +1 is -1, -1 into -1, that is +1, -1 into +1, that is -1, -1 into -1, that is +1. Same again here, 0 into all this will be 0. 4 zeros you will get in the sequence product. Okay, and then again this one, that is C4, you have D1, this 1 into all this, you will get the same sequence. Now all these sequences you have to add together to get this sequence, that is -1, -1, -3, +1. Each of this you have to add. See, for example, the first element of each sequence, -1, -1, you will get -2, isn't it? +1, it is -2, +1, it is -1, +0 plus -1 itself. Again, the second element from each sequence, that is -1, +1, it is 0, isn't it? Second sequence, okay. And 0 plus 0, 0, and the second one, that is -1. -1 is left, this is -1. Third one is -1 plus -1, it is -2, plus this -1, it is -3, plus 0, -3 itself. Fourth sequence, -1 plus 1, it is 0, and you have +1 here. +1 and 0, you will get adding, okay. You will get this +1. Now understood, right? How we are adding these four sequences, that is D1 C1 plus D2 C2 plus D3 C3 plus D4 C4, and this together forms this sequence which is sent as data through the common channel. Here it shows the digital signal created by 4 stations in CDMA, that is bit 0, which is from the first station. It has the sequence -1, -1, -1, -1, which is represented as, see, -1, -1, -1, -1, digital signal. Okay. Now bit 0, second station, has the sequence -1 +1 -1 +1. This is -1 +1 positive voltage, -1 negative voltage, +1 positive voltage. And the third station is silent, so it is idle station. This is 0. Okay. Next bit 1, fourth station has this sequence, that is +1 -1 -1 +1. Positive voltage, negative, negative, and plus. And this is the data on the channel, the resulting digital signal on the channel. This is according to this sequence, that is -1 -1 -3 +1. Here you have this, that is and right, this is first one here, this is -1, and this is -1 negative voltage, and say this is your -3, and this is +1. Okay, understood, right? Okay, now the next one is the Walsh table. We'll see what is this Walsh table. We saw the chip sequences, right? Now we need the chip sequences for this CDMA process. So general rule and examples of creating Walsh tables, that is, to generate chip sequences, we use a Walsh table, which is a two-dimensional table with an equal number of rows and columns. See here in the Walsh table, each row is equal to number of columns here. 2 rows, 2 columns. 4 rows and 4 columns here. Okay. And each row is a sequence of chips. For example, in our example it was 4 stations. Here if you see V4, you have 4 sequences. Each row, that is plus 1, plus 1, plus 1, plus 1, plus 1, minus 1, plus 1, minus 1, plus, plus, minus, minus, plus, minus, minus, plus. These are the 4 sequence we saw now, isn't it? So in the Walsh table, each row is a sequence of chips. Okay. Now W1 for a one chip sequence has one row and one column. Here you can either choose plus 1 or you can choose minus 4. Here for W1 we have to choose plus 1. Okay. Now according to Walsh, he says that if you know the table for n sequences, then that is Wn, then we can create the table for 2n sequences. This one. This is in general. Okay, this shows Wn with the that is this Wn. You can, if you know, say if this is n, that is 1 is n, then this is, you can create 2n, twice of this one. Same thing you have to use twice. Okay. Now W2 here. Now what is this Wn bar? When you have this Wn bar, all the bits you have to inverse it. That is, if you have plus 1, you have to represent it as minus 1, and vice versa. That is minus 1, you have to represent it as plus 1. Here it shows how we can create the Walsh tables, that is W1, W2, W4, how it is created. Okay, here in W1 you have one row and one column, and that is plus 1, and in W2 you have 2 rows and 2 columns. How many chip set sequence you have? 2. Each row is a sequence, isn't it? Chip sequence of chips, that is say your code, isn't it? If you have 2 stations, you can go for these sequences, plus 1, plus 1, plus 1, minus 1, that is C1 and C2, code C1 and code C2. Now from this W2 is plus 1, plus 1, plus 1 and minus 1, isn't it? Why minus 1 here? In general formula you have the inverse of Wn, that is inverse of this one, minus 1. From W2 you can create 2n, that is 2 into 2, that is W4 you can create, 2 into 2, that is W4. How W4 is created here? This is for 4 stations. You can create 4 chip sequences. How? Each row is a chip sequence. 1, 2, 3, 4 sequences you can get from this one. Okay. Now, how you are creating? You have W4. If you have a W2n, then each 3 times you have to place Wn. And once the inverse, isn't it? So here you have W4. 3 times you have to place this W2 here. See this yellow marks. This is the W2, isn't it? This you have to place it here 3 times. And the last one is the inverse of it. So what is the sequence here for W2? Plus 1, plus 1, plus 1, minus. So plus 1, plus 1, plus 1 and minus. Again plus 1, plus 1, plus 1 and minus. Same thing here also, plus 1, plus 1, plus 1 and minus 1. But here the fourth, this particular Wn you have to inverses. That is, see, here you have plus 1, right? So this is minus 1, inverse. This is plus 1, this is minus 1. Inverse of this one, that is minus 1. Inverse of this minus 1, that is plus 1. Inverse of this one, okay, that is W2 inverse it is. This is W2, W2, W2 and W2 inverse. Understood, right? How we are creating this W4. Again, if you want to create the next sequence, that is W8. 8 for 8 stations. If you have 8 stations, you need 8 sequences, right? That is, each row will be one chip sequence there. Now, what you have to do, you have to place W4 at all the places except the last one. There you have to inverse W4 inverse. You have to take the inverse of W4. That is how you create the chip sequences using this Walsh table. Why we are using this Walsh table? To generate the chip sequences. Where we use this chip sequence? In each station to multiply with the data sequence, isn't it? After finding the product of data and the chip sequence, you will take the arithmetic of all this and send through the channel in the form of data. That is the overall procedure what you are doing in this particular that is code division multiple access protocol. And what is the advantage of this code division multiple access protocol? It will send the data simultaneously, as well as it will utilize the entire bandwidth. Remember these 2 points. Okay, that is, it will utilize the entire bandwidth, and the second point, that is, it will send the data simultaneously. Hope you understood the topic till now. Thank you, students.